There is a rule in cosmology, a rule so fundamental, so deeply embedded in the mathematics of how we understand the universe, that without it, almost nothing in modern astrophysics works. It is called the cosmological principle, and it states simply that on large enough scales, the universe looks the same everywhere. No special places, no structures too large to exist. Just a smooth, even distribution of matter, galaxies here and galaxies there, in a pattern that averages out to uniformity when you zoom out far enough. Every cosmological model we have, including lambda CDM, the standard model of cosmology that guides our understanding of everything from the Big Bang to the present day, is built on this rule. Every equation that describes how the universe expands, how dark energy accelerates that expansion, how dark matter shapes the large-scale structure, all of it assumes, at the foundation, that the universe is not clumped beyond a certain scale. That scale has a name. Astronomers call it the homogeneity scale, and based on the best models of how structure forms from the seeds of the Big Bang, under the influence of gravity over 13.8 billion years, the homogeneity scale is approximately 1.2 billion light-years. 1.2 billion. That is the size of the largest structures the universe is theoretically allowed to contain. Above that scale, physics, as we understand it, predicts the universe must smooth out. In November 2013, a team of American and Hungarian astronomers announced they had found something that violated this rule by a factor of 8. They called it the Hercules-Corona Borealis Great Wall, a structure, a genuine, physically connected superstructure of galaxies and galaxy clusters, stretching approximately 10 billion light-years from end to end. 10 billion. The rule says 1.2 billion is the maximum. What they found was more than 8 times larger than the maximum, a structure so enormous that light, traveling at 300,000 kilometers per second, would take 10 billion years to cross it, nearly as long as the entire age of the universe. And then, in April 2025, the same team of researchers looked again, with a larger data set, more gamma-ray bursts mapped, better statistical methods, and they found that the original estimate, already impossibly large, was too small. The Hercules-Corona Borealis Great Wall may extend across 15 billion light-years of space, 50% larger than previously thought, and in some models, the structure could be even bigger than that. This is the structure that nobody can explain. The wall that should not be there, the thing that, if it is real, and growing evidence suggests it is, means either our understanding of how the universe formed is fundamentally wrong, or the universe itself played by different rules in the first few billion years of its existence. This is the full story. To understand why the Hercules-Corona Borealis Great Wall is such a problem, you first need to understand what the universe looks like on its largest scales. And to do that, you need to understand the hierarchy of cosmic structure, the architecture of the universe from individual stars all the way up to the cosmic web itself. At the smallest scale of cosmic structure, there are individual stars. Our Sun is one of roughly 200 billion stars in the Milky Way. The Milky Way itself is a large barred spiral galaxy, roughly 100,000 light-years across at its disk. It is not exceptional. There are perhaps 2 trillion galaxies in the observable universe. 2 trillion individual island universes of stars, gas, dust, and dark matter, each one containing anywhere from a few million to a few trillion stars of their own. Galaxies are not distributed randomly across space. They cluster. Gravity is the force that drives this clustering, pulling galaxies toward each other over billions of years. The Milky Way is part of a small cluster of roughly 50 galaxies called the local group. The local group is dominated by two large spirals, the Milky Way and the Andromeda galaxy, with dozens of smaller dwarf galaxies scattered around them. The local group spans roughly 10 million light-years in diameter. The local group is itself a member of a larger structure. The Virgo supercluster, also called Laniakea, is a vast gravitationally bound supercluster of galaxies that contains over 100,000 member galaxies across approximately 500 million light-years. Our entire local group, with all its 50 galaxies, is a tiny province on the outskirts of this supercluster. Laniakea was only fully mapped in 2014, when a team led by Brent Tully used galaxy velocity flows to define its boundaries. But Laniakea is not the largest thing we know about, not by a long way. On scales above superclusters, the universe organizes itself into what astronomers call the cosmic web, an interconnected network of galaxy filaments, walls, and voids that stretches across the entire observable universe. The filaments are dense concentrations of galaxies strung along the threads of the cosmic web, like beads on a wire. The walls are flat concentrations of galaxies at the intersections of multiple filaments, and between these structures lie the cosmic voids, vast, nearly empty regions of space, sometimes hundreds of millions of light-years across, containing almost no galaxies at all. This cosmic web is not random. It is the direct consequence of the quantum fluctuations in the very early universe. Tiny density variations in the primordial plasma, amplified by gravity over billions of years into the architecture we see today. The seeds of every galaxy, every cluster, every filament and void in the present-day universe were planted in the first fractions of a second after the Big Bang, in fluctuations so small that they are detectable in the cosmic microwave background as temperature variations of just 1 part in 100,000. The scale hierarchy goes stars, then galaxies, then galaxy groups, then galaxy clusters, then superclusters, then filaments and walls of the cosmic web, and at each level of the hierarchy, gravity is the architect. Each structure forms by gravity, collecting matter from the level below and assembling it into the level above. Now here is the critical point. Each level of this hierarchy has a characteristic scale, a typical size for the structures at that level. Galaxies are typically tens of thousands to hundreds of thousands of light-years across. Galaxy clusters are tens of millions of light-years. Superclusters reach into the hundreds of millions of light-years. And the largest filaments and walls of the cosmic web, based on computer simulations of structure formation under lambda CDM, should extend to at most a few 100 million light-years. Perhaps, in extreme cases, pushing toward 1 billion light-years. The theoretical maximum, the scale above which the universe is expected to be statistically homogeneous, above which no bound structures should exist, is approximately 1.2 billion light-years. The Sloan Great Wall, discovered in 2003 from the Sloan Digital Sky Survey galaxy data, was for a decade the record holder for largest known structure at approximately 1.3 billion light-years. It was pushing against the theoretical limit. It was noted as a potential problem, but still within the range where sampling effects and projection biases might explain the apparent size. Then came the huge Large Quasar Group. In 2013, a team led by Roger Close of the University of Central Lancashire announced the discovery of a clustering of quasars, the brilliant, high redshift nuclei of active galaxies, spanning approximately 4 billion light-years. 4 billion, more than 3 times the theoretical maximum. The astronomy community was divided. Many argued that the apparent clustering was a statistical artifact, that the quasars were not physically associated, just apparently clustered due to sampling effects in the survey data. Others argued the detection was real and demanded explanation. And then, 9 months later, came something larger. Something that made the huge large quasar group look modest. Something that, to this day, remains the largest known structure in the observable universe. The Hercules-Corona Borealis Great Wall. To understand how the Hercules-Corona Borealis Great Wall was found, you need to understand the tool used to find it. Not a telescope in the conventional sense. Not an instrument that looks at galaxies directly, but a survey of the most powerful explosions in the universe. Gamma-ray bursts. Gamma-ray bursts are the most luminous events in the cosmos. They occur when a massive star collapses in a core collapse supernova, or when two neutron stars merge after a death spiral lasting millions of years. In either case, the result is a brief, intense jet of gamma rays, the highest energy form of electromagnetic radiation, that fires outward from the collapsing or merging object at close to the speed of light. The initial burst can last anywhere from milliseconds to several minutes. The energy released in a gamma-ray burst is extraordinary. A typical burst releases more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. In its first fraction of a second, a gamma-ray burst can briefly outshine the combined light of all the stars in the observable universe. They are detectable from literally any distance within the observable universe, the most energetic individual events in cosmic history. And because they are associated with the deaths of massive stars, and massive stars are only found in galaxies, gamma-ray bursts are traces of galaxies, including galaxies too faint and distant for conventional telescopes to observe directly. This is the key. Gamma-ray bursts can be used as probes of large-scale structure in the same way that distant quasars are used, as bright beacons that reveal the presence of the galaxies in which they occur, at distances where those galaxies themselves would be too faint to study directly. And because gamma-ray bursts can be detected at redshifts of up to 9 or 10, meaning epochs when the universe was less than 1 billion years old, they probe the galaxy distribution across an enormous volume of cosmic history. The NASA Swift Gamma-Ray Burst mission, launched in November 2004, was designed specifically to detect and localize gamma-ray bursts with unprecedented speed and precision. Within seconds of detecting a burst in gamma rays, Swift automatically slews its X-ray and ultraviolet telescopes to follow up, capturing the fading afterglow of the burst and providing a precise position that allows ground-based observatories to measure a spectroscopic redshift, the distance to the burst. By the early 2010s, Swift had compiled a catalogue of hundreds of gamma-ray bursts with known redshifts, distributed across the observable universe. In 2013, a team of 3 astronomers, István Horváth of the National University of Public Service in Budapest, Hungary, John Hackler of the University of Alabama in Huntsville in the United States, and Zsolt Bergoli of Eötvös Loránd University, also in Hungary, were analyzing the distribution of gamma-ray bursts from the Swift catalogue. They were looking for statistical anomalies, patterns in the distribution that deviated from the smooth, random distribution expected if gamma-ray bursts trace a uniform galaxy distribution. What they found was not subtle. In a region of the sky corresponding to the constellations of Hercules, Corona Borealis, Lyra, Bootes, and Draco, they detected a concentration of gamma-ray bursts at redshifts between approximately 1.6 and 2.1. This redshift range corresponds to a cosmic epoch roughly 7 to 10 billion years ago, when the universe was between 35 and 50% of its current age. Within this redshift range, in this region of the sky, there were far more gamma-ray bursts than expected from a random distribution. The statistical significance of the clustering was high. The initial 2013 paper, published at the 7th Huntsville Gamma-Ray Burst Symposium, reported that the probability of the clustering occurring by chance was less than 1%. A follow-up paper published in 2014 in the journal Astronomy and Astrophysics, using a larger sample of bursts and more rigorous statistical methods, confirmed the result. The clustering was real, and the implied size of the structure producing this clustering was extraordinary. If the concentration of gamma-ray bursts reflected an underlying concentration of galaxies, the natural interpretation, given that gamma-ray bursts trace star formation in galaxies, then the structure responsible was approximately 2,000 to 3,000 megaparsecs in its longest dimension, 6 to 10 billion light-years, nearly 10 times the theoretical maximum for any structure permitted by the standard model of cosmology. The team named it the Hercules-Corona Borealis Great Wall, after the primary constellations in the direction of the structure as seen from Earth. And they published their finding with an appropriate degree of caution, acknowledging that the sample size was limited, that the redshift measurements carried uncertainties, and that alternative explanations needed to be considered. But the data was the data. Something was there. The discovery attracted immediate attention and immediate skepticism. Large-scale structure claims at this level of scale are inherently controversial, for reasons we will examine in detail later. But the original paper was peer-reviewed and published. The team presented their results at international conferences, and they began planning a follow-up study with a larger dataset to either confirm or refute the initial detection. That follow-up would take a decade. And when it came, in 2025, the news was not smaller, it was bigger. Let us be precise about the scale problem, because the numbers involved are so large that they become abstract, and it is only when you translate them into concrete comparisons that the full weight of what the Hercules-Corona Borealis Great Wall represents becomes clear. The Milky Way galaxy is approximately 100,000 light-years across. That means light, traveling at the fastest possible speed in the universe, takes 100,000 years to cross our galaxy from edge to edge. 100,000 years. Human civilization is roughly 12,000 years old. The Milky Way is 8 times wider than the entire span of human history in years of light travel. The Andromeda galaxy, our nearest large neighbor, is approximately 2.5 million light-years away. The local group, containing both the Milky Way and Andromeda and all their satellite galaxies, spans roughly 10 million light-years. The Virgo supercluster, of which we are a part, spans approximately 500 million light-years. The Sloan Great Wall, discovered in 2003 from the Sloan Digital Sky Survey galaxy data, and the previous record holder for largest known structure, spans approximately 1.3 billion light-years. In the context of the Virgo supercluster at 500 million light-years, the Sloan Great Wall is nearly 3 times larger. In the context of the distance to Andromeda at 2.5 million light-years, the Sloan Great Wall is 520 times larger. And the Sloan Great Wall was already considered a structure pressing against the theoretical boundary of what is allowed. Now consider the Hercules-Corona Borealis Great Wall at 10 billion light-years. It is approximately 7.7 times the size of the Sloan Great Wall. It is 20,000 times the size of the Virgo supercluster. It is 100,000 times the distance from the Milky Way to Andromeda. If you were to place it next to the Milky Way, a galaxy 100,000 light-years across, the Hercules-Corona Borealis Great Wall would be 100,000 times larger than our entire galaxy. To put it in another way, the observable universe has a diameter of approximately 93 billion light-years, the sphere within which light has had time to travel to reach us since the Big Bang. The Hercules-Corona Borealis Great Wall, at 10 billion light-years, spans approximately 1/9 of the diameter of the entire observable universe. 1/9, not a tiny fraction, not a statistically unlikely, but technically possible outlier. 1/9 of the entire observable universe, filled with a connected structure of galaxies. Why is this a problem? Because the theoretical maximum size for any gravitationally bound structure, derived from the equations describing how structure grows under the influence of gravity, dark matter and dark energy in a lambda CDM universe, is approximately 1 billion to 1.3 billion light-years. The details depend on the exact parameters assumed, but the consensus among cosmologists is that the homogeneity scale is somewhere in that range. The reasoning is as follows. Structure formation takes time. Gravity is not instantaneous. It works by accumulating mass over billions of years, pulling matter toward overdense regions and evacuating underdense regions. The rate at which this process operates is constrained by the expansion of the universe. As space expands, it works against gravity, preventing matter from clumping on scales above a certain limit. The faster the universe expands, the smaller the maximum structure size. And the universe, accelerating under the influence of dark energy, has been expanding faster and faster for the last several billion years. The calculation is not approximate. Lambda CDM makes specific testable predictions about the statistical properties of large-scale structure. It predicts the power spectrum, the distribution of structure sizes and amplitudes, with high precision. And that power spectrum predicts that density fluctuations on scales above 1 to 2 billion light-years should be negligibly small. The universe on those scales should be as smooth as freshly poured concrete. No clumps, no walls, no structures of any kind visible above the random statistical noise. A structure of 10 billion light-years is not a small violation of this prediction. It is not a marginal exceedance of the allowed limit, explainable by a slightly different parameter choice or a modeling uncertainty. It is 8 times larger than the maximum. If the Hercules-Corona Borealis Great Wall is real and physically connected, then either our model of structure formation is fundamentally wrong, or the universe formed its largest structures through a process we have not yet identified. And it is at this point that the debate about whether the structure is real becomes critical, because a discovery this dramatic demands extraordinarily strong evidence. The entire field of cosmology, half a century of theoretical and observational progress, is not going to be overturned by a single paper based on a few hundred gamma-ray burst positions. The skeptics have reasonable grounds for their skepticism, and the arguments on both sides deserve to be heard. But first, let us address what happened in 2025. Because the story did not stay at 10 billion light-years. The original 2013 discovery was based on analysis of 283 gamma-ray bursts with measured redshifts from the Swift catalogue. The follow-up 2015 paper expanded this to 361 bursts. In both cases, the statistical signal was clear. Something was concentrating gamma-ray bursts in the Hercules-Corona Borealis region at redshifts between 1.6 and 2.1. By 2025, the combined databases of the Swift satellite, the BATSI instrument on the Compton Gamma Ray Observatory, and the Fermi Gamma Ray Space Telescope had grown substantially. The total catalogue of gamma-ray bursts with known redshifts now reached 542 events, nearly double the sample of the original discovery paper. And in April 2025, Horvath, Hakala, Bergoli and their collaborators published a new analysis using this expanded dataset. The results, published as a preprint on Archive with identifier 2504.05354, were striking. The new analysis not only confirmed the original clustering signal, it found it to be more extensive than previously estimated. The best fit model for the structure's extent suggested a length of approximately 15 billion light-years in its longest dimension, with a transverse extent of approximately 7.2 billion light-years, 15 billion light-years, 50% larger than the previous estimate of 10 billion, and the researchers noted that under some modeling assumptions, the structure could be even larger, potentially extending to 30 or more billion light-years in some directions. These extreme estimates carry significant uncertainties, and the team was careful to present the full range of possible sizes consistent with the data. But the central value of the best fit model was 15 billion light-years, a number that exceeds the original estimate by half. The new analysis also found that the structure might be located somewhat closer to Earth than originally estimated. The original 2013 paper placed the overdensity at a mean redshift of approximately 2, corresponding to a distance of roughly 10 billion light-years. The 2025 analysis suggests the structure may be centered at a somewhat lower redshift, potentially making it closer to Earth than previously thought. This matters for the constraints on the maximum structure size, because a closer structure that appears as large on the sky would need to be physically even larger than the same apparent size at greater distance. Dr. John Hakila, speaking about the findings, noted that the expanded dataset provided stronger statistical confidence than the original detection. Each gamma ray burst in the catalogue represents a galaxy, a tracer of where matter is concentrated in the universe. With 542 bursts, the statistical power to detect a concentration is substantially higher than with 283. The signal strengthens with each new burst added to the catalogue. He also highlighted the importance of the forthcoming ESA space mission, Theseus, the transient high-energy sources and early universe surveyor. For the future of this research, Theseus is designed specifically to detect gamma-ray bursts at extreme distances, with the capability to measure redshifts automatically and assemble a catalogue of bursts many times larger than anything currently available. If approved and launched as planned, Theseus would provide the observational leverage needed to map the Hercules-Corona Borealis Great Wall in its entirety, to determine definitively whether the 15 billion light-year estimate is correct, or whether the structure is even larger. Hakila was explicit about what the 2025 data means for the theoretical problem. He said, and I'm paraphrasing from the paper's conclusions, that the expanded size estimate makes the challenge to the cosmological principle more severe, not less. A structure of 15 billion light-years is not incrementally harder to explain than one of 10 billion. Both are so far above the theoretical maximum that the difference between them is almost beside the point. What matters is that the homogeneity scale prediction of lambda CDM appears to be violated by a large factor, and the violation becomes clearer as more data arrives, not less clear. This is the direction that worries cosmologists. When a measurement becomes more significant as the sample size grows, when the anomaly strengthens rather than dissolves, it is a sign that the anomaly is real. Statistical flukes tend to fade as sample sizes increase. Real physical effects tend to solidify, and the Hercules-Corona Borealis Great Wall has been solidifying for 12 years through multiple independent analyses. Using multiple independent datasets, the skeptic's best remaining argument is sampling bias, the possibility that gamma-ray burst catalogues are incomplete in ways that artificially concentrate apparent bursts in certain regions of the sky. This is a legitimate concern, and we will examine it carefully in the chapter on competing theories. But first, let us go deeper into the theoretical problem. Because the cosmological principle is not just a cosmological nicety, it is the bedrock of everything. The cosmological principle is the founding assumption of modern cosmology. It states that the universe is, on sufficiently large scales, both homogeneous, the same everywhere, and isotropic, the same in all directions. This is not simply a convenient mathematical assumption. It is a philosophical statement about the nature of the universe, rooted in the post-Copernican worldview that we, our planet, our star, our galaxy, do not occupy any special position in the cosmos. The cosmological principle was first explicitly incorporated into cosmological models by Albert Einstein in 1917, when he applied his field equations of general relativity to the universe as a whole. To make the mathematics tractable, Einstein assumed that the universe, averaged over large enough volumes, was uniform in density. This assumption allowed the extraordinarily complex tensor field equations of general relativity, equations that in their full form describe the curvature of space-time at every point, to be reduced to a single, manageable equation describing the evolution of the universe's overall scale. From Einstein's application of the cosmological principle emerged the Friedmann equations, derived independently by Alexander Friedmann in 1922, which describe how the universe expands over time. Every cosmological model since then, from the steady-state theory of the 1950s to the inflationary Big Bang models of the 1980s to the lambda CDM concordance model of today, has been built on the Friedmann equations. And the Friedmann equations require the cosmological principle. Without it, the mathematics becomes intractable. If the universe is not homogeneous and isotropic on large scales, if it has significant structure on scales comparable to or larger than the Hubble length, then the simple scale factor description of the universe's expansion breaks down. The universe cannot be described by a single expansion rate, a single temperature, a single density. It becomes a patchwork of regions with different local expansion histories, different local densities, different local physical conditions, and the entire edifice of modern cosmology, the Big Bang, the cosmic microwave background interpretation, the constraints on dark matter and dark energy, needs to be rebuilt from scratch. This is why the cosmological principle is taken so seriously. It is not merely convenient, it is load-bearing. The entire theoretical structure of modern cosmology rests on it. And this is why the Hercules-Corona Borealis Great Wall is not just an interesting anomaly. It is a structural threat to cosmology if it is real and if it is as large as the data suggests. The theoretical expectation for the homogeneity scale comes from the theory of cosmological inflation. The rapid, exponential expansion of the universe in the first tiny fraction of a second after the Big Bang that is believed to have smoothed out any initial density variations and seeded the tiny quantum fluctuations that became the seeds of all subsequent structure. The amplitude and statistical properties of these primordial fluctuations, imprinted on the cosmic microwave background, determine how large a structure gravity can build in the 13.8 billion years since the Big Bang. The cosmic microwave background itself, the faint, almost perfectly uniform microwave glow that fills the sky in every direction, is the strongest evidence for the cosmological principle. measured with extraordinary precision by the COBE, WMAP and Planck satellites. The CMB is uniform to 1 part in 100,000. Its temperature, in every direction you look, is 2.725 degrees Kelvin. The tiny fluctuations from this mean are what became all the structure we see today. Every galaxy, every cluster, every filament, and those fluctuations, whose properties are so precisely measured, determine the maximum structure size. This is a key point. The CMB fluctuations are not just observed, they are theoretically predicted. Inflation predicts their statistical properties, called the power spectrum, with extraordinary precision, and the power spectrum predicts that density fluctuations on scales above about 1 billion light years should be minuscule, essentially zero at the scales relevant to the Hercules-Corona Borealis Great Wall. The Great Wall is claiming that gravitational amplification of a primordial fluctuation produced a structure at 10 to 15 billion light-year scales. For that to be possible under lambda CDM, the primordial fluctuation at that scale would need to have been enormously larger than the measured CMB predicts. There is one caveat to this analysis, which the defenders of the Great Wall's reality are careful to note. The cosmological principle is a statistical statement. It refers to the average properties of the universe over large volumes, not to any individual observation. In any realization of a stochastic process, and the distribution of matter in the universe is, on some level, a stochastic process seeded by quantum fluctuations, there will be rare, extreme outliers. A structure as large as the Hercules-Corona Borealis Great Wall might be an extraordinarily rare but not impossible fluctuation of an underlying process that is consistent with lambda CDM. The question is how rare, and estimates of the probability of finding a structure this large in a lambda CDM universe range from extremely small, parts in a million, to effectively zero. The exact number depends on assumptions about the survey geometry, the reliability of the gamma-ray burst sample, and the definition of what constitutes a physically connected structure. But even the most charitable estimates suggest that the Hercules-Corona Borealis Great Wall, if real, is a profound outlier from theoretical expectations. This brings us to the most fundamental question. What could possibly have produced this thing? And is there any model, any physical mechanism that could explain a structure at this scale? Let us suppose, for the sake of argument, that the Hercules-Corona Borealis Great Wall is exactly what it appears to be, a physically connected superstructure of galaxies and galaxy clusters, 10 to 15 billion light-years in its longest dimension, existing as a real bound or quasi-bound structure in the present-day universe. What physical mechanism could have produced it? What happened in the early universe that could have seeded a density fluctuation large enough and with enough time to grow to produce something at this scale? Within the standard framework of lambda CDM cosmology and single-field slow-roll inflation, the most conventional form of inflationary theory, in which a single scalar field called the inflaton drives the exponential expansion, the answer is essentially nothing. Standard inflation predicts a nearly scale-invariant spectrum of primordial fluctuations, fluctuations that are present at all scales, but whose amplitude decreases with increasing scale in a specific measured way. The CMB measurements pin down this spectrum with high precision, and those measurements leave no room for the enormous primordial fluctuation at the 10 billion light-year scale that would be needed to produce the Hercules-Corona Borealis Great Wall. But standard single-field inflation is not the only inflationary model. There is a large family of alternative inflationary theories: multi-field inflation, non-Gaussian inflation, inflation with features in the inflaton potential, that allow for enhanced primordial fluctuations at specific scales. In some of these models, the primordial power spectrum is not perfectly scale invariant, but has a bump or peak at a particular scale corresponding to a physical feature of the inflationary potential. If such a feature happened to occur at the scale corresponding to the Hercules-Corona Borealis Great Wall, it could have seeded a density, enhancement large enough to grow into the observed structure. This is not a theory invented to explain the Great Wall. It is a generic prediction of a broad class of inflationary models that have been studied for other reasons. Primordial features in the inflation potential are motivated by theoretical considerations, including the production of primordial black holes, the generation of gravitational waves at specific frequencies, and the solution to certain fine-tuning problems in inflation theory. If the Hercules-Corona Borealis Great Wall is real, it could be the large-scale observational signature of exactly this kind of inflationary feature. A second possibility involves the role of dark matter. The standard lambda CDM model assumes cold dark matter particles that are effectively non-relativistic at the time of structure formation, moving slowly relative to the speed of light. Cold dark matter clusters efficiently on small scales, providing the scaffolding for galaxy formation. But alternative dark matter models, including warm dark matter, with slightly higher particle velocities and self-interacting dark matter, in which dark matter particles can scatter off each other, can change the clustering properties of dark matter on various scales. In some dark matter models, the clustering of dark matter on very large scales is enhanced relative to the lambda CDM prediction. This could potentially produce larger structures than lambda CDM allows if the dark matter component of the universe was more concentrated on 10 billion light-year scales than standard calculations predict. The constraints on dark matter properties from other observations, the Lyman alpha forest, the mass function of galaxy clusters, the properties of dwarf galaxies, limit how different dark matter can be from the CDM prescription. But within those limits, some enhancement of large-scale power is possible. A third and more radical possibility involves a modification of general relativity itself on cosmological scales. The standard cosmological equations assume that Einstein's general relativity correctly describes gravity on all scales, from the scale of the solar system, where it has been tested to extreme precision, all the way up to the scale of the observable universe. But there is no guarantee that this is the case. On cosmological scales, scales of billions of light years, general relativity has never been tested directly. Modified gravity theories, in which the gravitational force law deviates from general relativity on very large scales, are actively studied as potential explanations for dark energy. And some of these modifications can also affect large-scale structure formation. There is also a possibility that does not require any new physics at all, but requires a fundamental revision to how we interpret our observations. This is the possibility that the universe is not homogeneous and isotropic on the scales we observe, but that we are located in an unusually underdense region, a cosmic void, that makes the universe around us appear to have different properties than it would to an observer in a typical region. This scenario, called the local void or Hubble bubble hypothesis, has been proposed as an explanation for the Hubble tension, and it could also contribute to making large-scale structures appear even more extreme than they would to an average cosmic observer. None of these explanations is the consensus view. The consensus view remains that the Hercules-Corona Borealis Great Wall is either a statistical fluke of an incomplete gamma-ray burst catalogue, or a projection effect in which physically unrelated structures at different distances appear superimposed on the sky due to the limited redshift precision of the observations. And we must give those skeptical arguments their full weight. Because in science, the burden of proof for a claim that breaks 50 years of cosmological theory is appropriately high. The debate about the reality of the Hercules-Corona Borealis Great Wall has been ongoing since 2013, and it remains unresolved. To evaluate the competing claims fairly, we need to understand both the evidence in favor of the structure and the most serious objections to it. The case for the structure's reality rests on three main pillars. First, the statistical significance of the gamma-ray burst clustering has been confirmed by multiple independent analyses. Using different statistical methods and different subsets of the data, and the significance has generally increased rather than decreased as the sample size has grown. Second, the phenomenon is persistent across different gamma-ray burst catalogues. Not only the Swift data, but also Fermi and Batsy data, suggesting it is not an artifact of any single instrument's observational biases. Third, the redshift range of the clustering, 1.6 to 2.1, corresponds to a specific epoch in cosmic history, and the clustering is concentrated in a specific region of the sky, not distributed randomly. These features are more consistent with a real physical overdensity than with a systematic artifact. The case against the structure's reality, or at least against its interpretation as a single physically connected entity, rests primarily on the quality of the data. Gamma-ray burst redshifts are typically measured from afterglow spectroscopy, a technically demanding observation that requires rapid telescope response after the burst, and that is subject to measurement uncertainties that can be substantial. A burst incorrectly assigned a redshift of 1.8 when it is actually at 2.5, for example, could appear to be part of the clustering when it is actually at a different distance. Furthermore, gamma-ray burst catalogues are incomplete. Not every gamma-ray burst has a measured redshift. Indeed, only a fraction do, because measuring a spectroscopic redshift requires rapid follow-up with a ground-based telescope. And this is not always possible. The bursts without redshifts are systematically different from those with redshifts. They tend to be fainter, shorter, or occurring in directions where rapid follow-up is harder. This incompleteness can, in principle, introduce biases into the apparent distribution of bursts with known redshifts. The most detailed challenge to the Great Wall came from Samuel Christian, a researcher who in 2020 published a critical reanalysis of the gamma-ray burst clustering evidence. Christian argued that when accounting for selection effects, including the non-uniform sky coverage of gamma-ray burst detections, the seasonal biases in ground-based follow-up observations, and the uncertainties in individual redshift measurements, the statistical significance of the clustering was substantially reduced. In some of his analyses, the significance dropped below the conventional threshold for a confident detection. The original team responded with an updated analysis that addressed several of Christian's concerns, while maintaining that the core signal remained significant. They applied more sophisticated statistical corrections for the selection effects Christian had identified and showed that, while the corrections reduced the significance somewhat, the clustering remained statistically robust under the most careful treatment of the data. The debate has not been definitively resolved by either side. What both sides agree on is that the current gamma-ray burst catalogue is insufficient to definitively confirm or rule out the Hercules-Corona Borealis Great Wall as a physical entity. 542 bursts with known redshifts, distributed unevenly across the sky, with varying redshift measurement uncertainties, simply do not provide the statistical power needed to settle the question What is needed is a much larger, more uniformly sampled catalogue, one that covers the full sky with consistent sensitivity and provides redshifts for a much higher fraction of detected bursts. There are also alternative observational approaches that could shed light on the question. Galaxy redshift surveys, direct catalogues of millions of galaxy positions and distances, are the most direct way to map large-scale structure. The Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and the ongoing Dark Energy Spectroscopic Instrument Survey have mapped hundreds of millions of galaxies. But these surveys have limited depth. They become incomplete at the high redshifts corresponding to the Hercules-Corona Borealis Great Wall, where individual galaxies are too faint to be catalogued with current instruments. The Vera Rubin Observatory, the Large Synoptic Survey, telescope under construction in Chile, will eventually image billions of galaxies to depths significantly greater than the Sloan survey, potentially reaching the redshift range of the Great Wall. The Euclid mission, launched in 2023, is conducting a spectroscopic and photometric survey of billions of galaxies across a wide area of the extragalactic sky, and the forthcoming Roman Space Telescope will conduct infrared surveys of the high redshift universe with unprecedented sensitivity. Each of these instruments will, over the coming decade, produce data that could directly test the existence of the Hercules-Corona Borealis Great Wall using galaxy positions rather than gamma-ray bursts. If the Great Wall is real, if there is genuinely an overdensity of galaxies in the Hercules-Corona Borealis region at redshifts 1.6 to 2.1, then these surveys should detect it. If it is an artifact of gamma-ray burst sampling biases, the galaxy surveys should find no corresponding overdensity. This is the clean scientific test that the debate needs, and it is coming. James Webb Space Telescope cannot directly confirm or deny the existence of the Hercules-Corona Borealis Great Wall. That is important to state clearly. JWST's field of view is tiny. It looks at very small patches of sky with extraordinary depth, not wide areas. Mapping the large-scale distribution of galaxies across 10 billion light-years requires either very wide-area surveys or a statistical tracer like gamma-ray bursts that can sample the whole sky. JWST is neither of these, but JWST can do something that matters deeply for the debate. It can observe individual galaxies at the redshifts corresponding to the Great Wall, redshifts between 1.6 and 2.1, with the spectroscopic detail needed to understand their properties, their environments, and their relationship to the large-scale structure they inhabit. And it can, in deep fields that coincidentally fall within the Great Wall's sky footprint, provide ground truth about the density of galaxies in that region. JWST's first deep field images, released in July 2022, showed thousands of galaxies in a tiny patch of sky that falls within the Hercules-Corona Borealis region of the sky. The specific field, known as SMACS 0723, is not a targeted observation of the Great Wall. It was chosen as an early demonstration field for entirely different reasons. But the galaxies visible in that image, at redshifts from less than 1 to greater than 13, include objects at the redshift range of the proposed Great Wall. And the density of galaxies visible in that field provides a data point, albeit a single, small data point, on the galaxy distribution in that region of the universe. JWST's spectroscopic capabilities are also relevant to the debate in a different way. One of the challenges with the gamma-ray burst mapping approach is the precision of individual burst redshifts. Many bursts have redshift measurements, accurate to only 1 or 2 significant figures, meaning a burst at a true redshift of 173 might be assigned a redshift anywhere from 1.6 to 1.9 depending on the quality of the spectroscopic data. This uncertainty smears out the apparent clustering in the radial direction and could, in principle, make a clustering that is less significant in three-dimensional space appear more significant in projection. JWST's NR-spec instrument, the near-infrared spectrograph, is capable of measuring redshifts to 5 or more significant figures for objects bright enough to observe. For gamma-ray burst afterglows at high redshifts, JWST could, in principle, provide redshift measurements of extraordinary precision in the critical few hours after a burst is detected. The challenge is operational. The telescope needs to be repointed rapidly to observe a burst afterglow before it fades, and JWST's Q-based scheduling does not currently support rapid target of opportunity observations in the way that ground-based observatories can. But this is a technical constraint, not a fundamental one. The mission that could most directly address the Hercules-Corona Borealis Great Wall question in the coming decade is Theseus, the transient high-energy sources and early universe surveyor is a proposed ESA medium-class mission that would monitor the entire sky for gamma-ray bursts, with the specific capability to measure redshifts autonomously for a much higher fraction of detected bursts than any current instrument. Theseus would detect roughly 1,000 gamma-ray bursts per year with known redshifts, compared to the approximately 40 per year that current missions achieve. Over a 5 to 7 year mission, Theseus would produce a catalogue of 5,000 to 7,000 gamma-ray bursts with known redshifts, 10 to 15 times the size of the dataset that currently exists. With this catalogue, the statistical power to map large-scale structure using gamma-ray bursts would increase dramatically. If the Hercules-Corona Borealis Great Wall is real, Theseus would detect it with overwhelming statistical confidence. The signal would be unmistakable if it is a sampling artifact or projection effect. The much more complete sky coverage of Theseus would dissolve the apparent clustering into the expected uniform distribution. Hakila, in papers and interviews discussing the 2025 results, has been explicit that Theseus is the instrument he is waiting for. He has said that the current data is suggestive but not definitive, that the signal exists and is statistically significant, but that the sample size and sky coverage of current catalogues leave enough room for skeptics to argue about sampling effects. Theseus would remove that argument. Either the structure is there, and Theseus will map it in detail, or it is not, and Theseus will demonstrate that convincingly. Beyond Theseus, the European Extremely Large Telescope and the 30-meter telescope, ground-based optical observatories currently under construction, will be capable of obtaining spectra of individual galaxies at the redshifts of the Great Wall in reasonable observing times. They will not be able to map the full extent of the structure. That requires a wide-area survey, not a large but narrow-field telescope, but they can confirm whether specific regions of the sky contain galaxy overdensities consistent with the Great Wall's predicted position and extent. The Euclid satellite, already in operation, is conducting a wide-area spectroscopic survey of galaxies out to redshifts of approximately 2, exactly the range of the Hercules-Corona Borealis Great Wall. Over its 6-year mission, Euclid will map billions of galaxies across 15,000 square degrees of extragalactic sky. Whether its survey footprint overlaps with the proposed Great Wall region is not certain, but the depth and coverage of the Euclid survey makes it a potential definitive test of the structure's existence. The next decade, in short, will likely resolve one of the most profound open questions in modern cosmology. Either the Hercules-Corona Borealis Great Wall will be confirmed by multiple independent observations using galaxy surveys, gamma-ray burst catalogues, and precision spectroscopy. In which case, the implications for the standard model of cosmology are far-reaching and will demand a fundamental revision of our understanding of structure formation, or it will dissolve under more careful scrutiny. The apparent clustering explained by sampling biases and projection effects, and the cosmological principle will emerge from this challenge intact, and perhaps stronger for having been so thoroughly tested. Either outcome is scientifically valuable. Science advances not just when theories are confirmed, but when they are seriously challenged. The Hercules-Corona Borealis Great Wall, whether real or not, has driven a decade of careful work on the statistical methods for detecting large-scale structure, on the systematic biases in gamma-ray burst surveys, and on the theoretical predictions of structure formation models. This work has value regardless of the final verdict on the Great Wall itself. But if it is real, if 15 billion light-years of connected cosmic structure genuinely exists out there, a tenth of the way across the observable universe, then we are living at a moment of genuine scientific revolution. There is something quietly extraordinary about the position we find ourselves in. We live on a planet orbiting a star. That star is one of 200 billion stars in a galaxy. That galaxy is one of 2 trillion galaxies in the observable universe. The observable universe spans 93 billion light-years in all directions from where we sit. And somewhere in that vastness, in the direction of Hercules and Corona Borealis, 10 billion light-years from where you are reading this, there may be a structure so enormous that it cannot, by our best calculations, have formed by the same processes that formed everything else we have ever observed. The Hercules-Corona Borealis Great Wall, if it is what the data suggests, is not just the largest known structure in the universe. It is a message written in the distribution of gamma-ray bursts and the positions of billions of galaxies, a message that has been traveling across 10 billion light-years of space and time, arriving in our detectors and our data catalogues, telling us something about the universe that we do not yet fully understand. Perhaps it is telling us that the early universe was more clumped, more structured, more complex than our models allow. Perhaps it is telling us that inflation, the rapid expansion that we believe, smoothed the primordial universe and seeded its structure, operated differently on the larger scales than on the smaller scales where we have measured it most precisely. Perhaps it is telling us that dark matter clusters differently than we assumed, or that gravity behaves differently at cosmic distances, or that we are looking at the sky through the lens of our own position in an unusually empty region of the universe. Or perhaps, and this must be said, it is telling us nothing at all. Perhaps the wall is not there. Perhaps when Theseus launches and surveys the sky with its superior sensitivity and sky coverage, the clustering will dissolve. The Hercules-Corona Borealis overdensity will prove to be a sampling artifact, and the cosmological principle will emerge unscathed from its most severe recent challenge. Science requires this possibility to be taken seriously. But this much is certain: the question itself is magnificent. The fact that we have found, or think we have found, something at the edge of what is physically allowed, something that sits at the intersection of the largest scales we can observe, and the deepest questions we can ask about how the universe works, is a testament to what science does. It does not just confirm what we think we know. It reaches further. It always reaches further. And sometimes, in the reaching, it finds something that requires the map to be redrawn. The universe is under no obligation to be kind to our theories. It has its own rules. Rules that we are slowly, painstakingly learning by looking harder and farther than anyone has looked before. James Webb, Euclid, Theseus, Roman, the extremely large telescope. These are the instruments of the next chapter of that learning. Each one will see further than the last. Each one will add data points to the question of whether the Hercules-Corona Borealis Great Wall is the universe's most profound anomaly, or its most elegant lesson in statistical humility. Either way, we will know. Within a decade, the answer will be clearer. Within 2 decades, it may be definitive. And when it is, the story of the Great Wall, whether it ends in confirmation or dissolution, will have been worth telling, because it forced us to look at the largest scales we can see, to question the most fundamental assumption in all of cosmology, and to ask, seriously and rigorously, whether the universe is as smooth as we assumed. The wall is there, waiting, 10 billion light-years away, in the direction of Hercules and Corona Borealis, stretching across the face of the universe like a scar, or a signature, or a question that the cosmos has been quietly asking since the Big Bang. We are only now learning to hear it. If this changed something in how you see the universe tonight, if it made the sky feel larger and stranger than it did before, please subscribe, because the universe has more questions like this one, and we are going to ask every single one of them